Welcome back to The Explainer. Today we're unpacking what is quite literally a life-or-death challenge at the very cutting edge of autonomous vehicles. We're going to look at exactly how engineers are teaching self-driving cars to see and perfectly recognize the world around them, whether they happen to be navigating from a low-riding sports car or sitting way up high in a massive 18-wheeler. It's a fascinating problem, so let's get into it.
Okay, let's dive into this. For a human driver, recognizing a car on the road is just totally effortless. It really doesn't matter if you're crouching down low in a tiny sedan or sitting way up high on the balcony of a transport truck, your brain just instantly knows, yep, that's a car. But artificial intelligence? Well, it doesn't work that way. If an AI perception system is trained entirely on data gathered from the low-riding cameras of a standard sedan, it gets completely confused when you suddenly take those exact same cameras and mount them way up high on the windshield of a semi-truck. The perspective shifts, the angles totally change, and suddenly the AI struggles to recognize the vehicles right in front of it.
So that begs the question. If a self-driving brain learns to drive in a sedan, what actually happens when you drop it into a truck? Well, historically, performance just completely plummets. And like we said, this is a literal life-or-death engineering challenge for advanced driver assistance systems. Now, the obvious solution might seem to be, hey, let's just collect brand new training data from scratch for every single vehicle type out there. But think about the logistics of that. Physically driving every single model of SUV, truck, and van millions of miles just to gather and hand-label new data? That is logistically exhausting, way too slow, and honestly, impossibly expensive.
To solve this, we first really need to understand the brain of our operation. Enter YOLO 8. YOLO stands for You Only Look Once, and it's a state-of-the-art, real-time object detection model. Basically, it's the highly sophisticated combination of eyes and brain that autonomous systems use to instantly spot other vehicles on the road. It uses this really advanced neural network architecture to perfectly balance extreme processing speed with incredibly high accuracy. And that's exactly what you need when you're hurtling down the highway at 70 miles per hour and you have to make split-second, life-saving decisions.
Now, what's really interesting here is that when YOLO V8 looks at a frame of video, it doesn't just see a flat picture like we do. Notice the bounding boxes instantly snapping around the vehicles. In mere milliseconds, it's extracting features, calculating spatial relationships, and identifying hazards. But remember, and this is key, YOLO V8 is only as good as the data it was originally trained on. If it has never seen what a car looks like from a really high-angle camera, those neat little bounding boxes might just completely fail to appear when they are needed most.
For years, engineers desperately tried to teach the AI new tricks using what we call traditional data augmentation. They take their existing sedan dataset and try to manipulate those 2D images. They'd flip the photos horizontally, crop them, zoom in, maybe change the color saturation a bit. But they quickly realize this completely fails. Because simply flipping a picture of a car doesn't teach the AI what the car actually looks like from 3 feet higher up in the air. These traditional methods lack what we call geometric adequacy. They just simply cannot mimic actual real-world 3D perspective shifts.
Which brings us to a massive breakthrough. We're finally moving away from that traditional augmentation, which basically just distorts 2D reality, and we're introducing an incredibly advanced new toolkit. We call it Novel View Synthesis, or NVS. Instead of just cropping a flat photo, NVS literally teaches the AI to imagine complex scenes from entirely new, unseen physical perspectives. It is structurally accurate, 3D imagination.
Think of it kind of like this. NVS takes a single, flat, 2D source image of a car on the highway. Then, using some really complex algorithms, it essentially hallucinates what that exact same car in that exact same lighting would look like if the camera were suddenly shifted up, down, left, or right to a new target pose. It's synthesizing a brand new, hyper-realistic image from a viewpoint that the camera never actually even captured.
So how exactly does it pull off this magic trick? Well, the secret lies in depth maps. A depth map is essentially a translation key, where the pixel colors literally dictate 3D distance. Typically, lighter colors mean an object is closer to the camera, while darker colors mean it's farther away. By generating an accurate depth map right alongside the original image, NVIDIA allows the computer to break out of the flat, two-dimensional constraints of the photo and start understanding the scene as a real, explorable, 3D physical space. Let's move along and see how this builds into a working methodology. One big approach is point cloud transformation. Here's how it works. First, the system reads the 2D image and our new depth map. Second, using the camera's intrinsic parameters, it maps every single pixel into a true 3D coordinate system, creating this dense cloud of points. Third, it mathematically shifts the virtual camera angle inside that 3D space, and finally, it reprojects all those 3D points back down into a brand new flat 2D image. It is literally turning pixels into a movable 3D world, shifting the camera, and then snapping a new photo of it.
But wait,
Point cloud transformation actually isn't the only way to do this. There's a competing NBS technique called multiplane images, or MPI, and this is super cool. Instead of moving individual 3D points around, MPI dynamically slices the scene into a stack of flat 2D image planes at varying depths. It's almost like a theatrical stage set made out of different layers of cardboard cutouts. While point clouds offer incredibly precise geometric control, MPI is just highly efficient and adaptive, making it absolutely fantastic for fast, high-quality rendering. To figure out which method is actually the best for training our self-driving cars, researchers put them head-to-head using what we can just call the reality check scores. These are rigorous reconstruction quality metrics. First, we have PSNR, which measures the peak signal against corrupting noise. Then there's SSIM, the Structural Similarity Index, which checks if elements like contrast and luminance actually match human perception. And finally, MSE, or mean squared error, which simply calculates the raw pixel-by-pixel error. Essentially, this is the ultimate test to see which method's hallucinated image most perfectly matches reality.
And the clear winner? MPI-based NVS. Across the board, the multiplane image method absolutely crushed the point cloud approach. It delivered higher visual fidelity, much better structural similarity, and importantly, noticeably fewer visual artifacts. It produced the most flawless, hyper-realistic artificial viewpoints for our AI to study. So the absolutely crucial point we need to look at is this specific number, 0.8 meters. Armed with that winning MPI technique, researchers went ahead and generated a massive new dataset where the virtual camera height was intentionally increased by 0.8 meters. Now, this specific height isn't random at all. It perfectly mimics the dramatic, real-world perspective jump from a low-riding sedan all the way up to a towering commercial truck.
And this sets the stage for the final road test. We have our advanced YOLO-VATE object detection model, and we have thousands of brand new synthesized images showing the world from exactly 0.8 meters higher up. The engineers then fed these extreme, entirely imagined viewpoints right back into the YOLO-V brain. The big question was, could the AI actually adapt to this massive simulated blind spot shift and still safely recognize the vehicles?
Get this, the results were nothing short of spectacular. The model miraculously maintained an incredible 99.5% accuracy rate at the standard intersection over union threshold. By simply studying those hallucinated MPI images, the YOLO-V8 model successfully adapted to the massive camera shift. It definitively proved that it could seamlessly generalize its understanding of vehicles to entirely new, unseen camera heights without needing a single real-world photo from a truck's perspective. How amazing is that?
So why does all of this matter for you and the future of transportation? Because this breakthrough fundamentally changes how we build autonomous systems. It entirely eliminates the need for expensive, repetitive, real-world data collection every single time a new car model rolls off the assembly line. It makes the technology highly scalable. You train the core model once and use this imagination to adapt it to literally any vehicle shape, size, or camera mounting. Most importantly, it dramatically increases road safety by proactively erasing dangerous AI blind spots before the car even hits the pavement.
Which leaves us with a truly fascinating thought to wrap up on. If artificial intelligence can now successfully imagine completely realistic visual perspectives it has never actually seen, what other senses could we teach it to hallucinate to keep us safe? Like, could we synthesize audio data to teach a car how to hear an approaching ambulance in a really complex acoustic environment? The boundary between what an AI actually experiences and what it can imagine is completely blurring, and that is absolutely going to make the self-driving cars of tomorrow vastly more capable. Thanks for joining me on this explainer, and keep questioning the world around you.